Hi everyone, and welcome to this video. In this lesson we're going to look at applications of the derivative, and we're going to start with absolute extrema. Let's define absolute maximum or minimum. Okay, we're going to let f be a function defined on some interval. And we're going to let c be a number in that interval. Okay, if f of c is the absolute maximum of the function in the interval, that tells me that f of x is less than or equal to f of c. Okay, so we would have an absolute maximum. So what that means is if you were to take a look at the graph here, here's my interval, let's say from x1 to x3, and let's say this is c, right? If f of x, which is the function, is less than or equal to f of c, then you have an absolute maximum. And if f of x is greater than f of c, we have an absolute minimum. So again, here's your absolute minimum, right? And we have f of c, so we'll pretend that this is c here, and we know that f of x is going to be greater than or equal to this value here, right? That's the lowest value, so that tells me that's an absolute minimum. It's the lowest point on that curve in that interval. And here's some other graphs where we have absolute maximums and minimums. So here we have another absolute minimum, right? And we can see that f of x, which is the rest of this graph, all of these y values are going to be greater than this y value. And here for this absolute maximum, all of these y values are less than this y value. So that's an absolute maximum. And again, you can see this here. You have this x value here, which is c, and all of these y values are going to be greater than or equal to this value. So that tells me that's a minimum, whereas all of these y values are less than or equal to that value. So that's a maximum. Okay, and of course that's for every x in the interval. When you hear the term absolute extrema, extrema is plural for extreme points, right? And we're referring to maxes and mins. Absolute maximum would be the highest point on that curve in that interval, and absolute minimum would be the lowest point on that curve in that interval, okay? When we're talking about maxes and mins too, we're really talking about the numbers, not the points. So it would be the y values. It can have any points where these values occur. So if you were to have the graph of f of x equals 2, that would be just a horizontal line through y equals 2. And as you can see there, that y value, which could be a max or a min, has occurs at every x value in some interval. Okay, so when we're talking about absolute maxes and mins, again, we're talking about the y values and not specific points. We have an important theorem here called the extreme value theorem, which I'll abbreviate as EVT. And the extreme value theorem says a function, again f, that is continuous on a closed interval and we'll call that interval AB just to make it easy, we'll have both an absolute maximum and an absolute minimum on that interval. So you can see in figure A, we have a continuous function, okay? And I know that because there's no breaks in the graph and you can draw this curve without lifting your pencil. It's on an open interval from A to B, okay? And it has an absolute minimum at x1, but no absolute maximum, okay? Because the graph goes on forever, right? So there is no ultimate high point there. And in figure B, it's discontinuous. Okay, I mean, I have to lift my pencil to draw the curve, and you can see this break in the graph there. A discontinuous function may or may not have an absolute max or min, right? So here you can see this has an absolute minimum right here at x equals a, because that's the lowest point. So it's the absolute minimum. But again, there's no absolute maximum. This point would be the absolute max, but it's an open circle. So we can't include that y value because the function is not defined there. Okay, so let's see how we can apply the extreme value theorem to finding absolute extrema. To find the absolute extrema for a function f that's continuous on a closed interval AB, okay, remember this is a closed interval, which is why we're using brackets. You want to find all critical numbers for f in the open interval AB. Right, so again, I want to make sure we're all clear on this. This is a closed interval, and then this is an open interval. Okay, so first we find all the critical numbers for f in the open interval. Then we're going to evaluate f for all those critical numbers. So similar to what we were doing in the past with the first and second derivatives. And then we're going to evaluate f for the endpoints a and b of the closed interval. And then the largest value found in step 2 or 3 is the absolute maximum for f on the interval, the closed interval, AB, and the smallest value found will of course be the absolute minimum. Okay, so let's try applying that here. Find the absolute extrema of the function f of x equals x to the 8/3 minus 16x to the 2/3 on the interval from -1 to 8. Okay? So I know that this function here isn't going to be undefined anywhere. So I know that it's continuous on the closed interval from a to b, in this case from -1 to 8. So I know the extreme value theorem applies. Okay, so the first thing I'm going to do is look for the critical values or critical numbers on the interval from -1 to 8. Okay, the open interval. Okay, so to find critical values, we know we have to find the derivative. So if I want to find the derivative, I'm just going to use the power rule. It's going to be 8/3 x to the 5/3. And then it's going to be minus 32/3 x to the -1/3. So let's see here. We can factor out an 8/3. And I can also factor out a -1/3. So if I divide 8/3 x to the 5/3 by 8/3 x to the -1/3, 8/3 divided by 8/3 just cancels out. 5/3 minus -1/3 is actually 6/3, which is 2. So I get x squared. And then if I divide -32/3 divided by 8/3, I'll get 32/8, which is 4, and it's negative, and then the x's cancel. And then I can just rewrite this as 8/3 times x squared minus 4 over x to the 1/3. Okay, so we're going to set that equal to 0, right? Looking for critical values. 8/3 can't equal 0, so I'm not going to worry about that. If I was to take this fraction and set it equal to 0, a fraction equals 0 when the numerator is 0. So I'm going to just take x squared minus 4, set it equal to 0, and I would get x equals plus or minus 2. Okay, now if I'm looking on the open interval from -1 to 8, -2 is not in that interval. So we're just going to forget about that. Okay. So 2 is going to be one of my critical values, and 0 has to be my other one because x could be 0, and that would make the function undefined. So I've got two critical values. One of them is 0, the other one is going to be 2. And 0 and 2 are both in the interval. Okay, so here's my critical values. And then I'm going to pick some test points. Okay, and I have a chart already kind of made for us to see here. So we've got maybe one of my test points could be -1. And then I can also pick, let's see, I don't really have to pick a number in between 0 and 2. I'm going to pick 8. Okay, and the reason I'm using those values is because they're my endpoints in the interval. Okay, so you're not worried about anything in here, not looking for maxes and mins, or so I'm going to use -1 and 8 because they're my endpoints, and then my two critical values, 0 and 2. And we're going to take these values and plug them into our normal function, right? So into f. So if I was to go to my calculator, hopefully no ads will come up. Go into y equals, clear out what's in there, and let's plug in our function. So it was x to the 8/3 and then it was minus 16x to the 2/3. Okay, make sure you hit enter. And then I'm going to check the table. So go to second table set, make sure for independent it says ask, which it does. And then go to second table. And then I'm going to delete these. And I'm just going to use the values that were in our table, -1, 0, 2, and 8. So -1, 0, 2, and 8. Okay, so those are the values that we get, which I'm going to then copy into our table. And all I want to do now is scan this, and I can see that this function here, when I plugged in 8, I got 192. That's the highest y value of all of the y values. So that tells me that this is a absolute maximum. And then when I compare the other values, I can see that this is the lowest. So that would be the absolute minimum. Okay. So now if I look at this graph from -1 to 8, of course, I'll be able to see this. So it helps to look at the graph. So we had x to the 2/3, or sorry, x to the 8/3. And then it was minus 16, x to the 2/3. Okay, and I'm only looking from -1 to 8. So let's see if this will let me I don't think I can change the window on here. So we're only looking from -1 to 8. Okay, so keep that in mind. So the lowest point there, right, you can see when it's -1 would be really helpful if I could actually change the viewing window here. But I don't know if it's going to let me. Oh, yes. Okay, so we'll make this -1. Oh, sorry. So for y, I'm not going to change it. Maybe for y, I'll do like -20. And then I'll do to like 200. And maybe I'll count by tens. And then for x, it's just going to go from -1 to 8. -1, +8. Okay, now we can see here, right? So if we take a look at the graph, if we're only looking from -1 to +8, we can see here that the lowest point is around what we came up with. It should be -19.05 for -1. And then for the highest point on the graph, when it goes to 8, it's telling me that the maximum is about 192. Okay. Here's a problem for you all to try. And then you can unpause the video when you're ready to move on. We'll move on to example number 2. So in example number 2, it says find the locations and values of the absolute extrema, if they exist, for the function f of x equals 2x to the fourth minus 16x squared plus 2. Okay, so here, notice they don't give us an interval, right? We have a polynomial function, so the extreme value theorem does not apply since the domain is an open interval from negative infinity to infinity. It's not like in the last example where we looked at on the interval -1 to 8 and it was a closed interval. So we can't necessarily apply the extreme value theorem, which remember said a function f that's continuous on a closed interval will have both an absolute maximum and an absolute minimum on that interval, which we saw in this last example, okay? We saw that it had an absolute min, and that was -19.05, and it also had an absolute max at 192. And it's because it was continuous, it was a continuous function, and it was on a closed interval. So here we have a continuous function, but it's not on a closed interval. So the extreme value theorem does not apply. All right, but I'm still going to go through my steps here to find the absolute extrema. I'm going to first find my first derivative, which would just be 8x to the third minus 32x. Okay, and we're going to set that equal to 0. So I can factor out a 8x, and I'm left with x squared minus 4. And then if I set my factors equal to 0, I get x equals 0, -2, and +2. Okay, so I'm going to make a little kind of like a table like I had provided for you all before. So x value and then value of f. And I'm going to just use my critical values there. Okay. And if you plug this in, if I plug in -2 back into my function, again, you can use the table in the calculator if you want, which I showed you how to do in the last example. You would get -30. And if you plug in a 0 into your original function, you're just left with 2. And if you plug in a +2 into the original function, you get -30. Okay, so this tells me here that there's an absolute minimum, and they're both the same number, right? So we have an absolute minimum there of -30. Now this graph is continuous, right? And we know by looking at this graph, the lead coefficient is a positive and the degree is even, which means the graph's going to go up on both sides, right? Both ends. So that tells me that there is no absolute maximum, okay? For an open interval, rather than evaluating the function at the endpoints, we evaluate the limit of the function when the endpoints are approached. And we know that the limit as x approaches infinity of that function, 2x to the fourth minus 16x squared plus 2, is going to also approach infinity. Okay, and we know that the limit as x approaches negative infinity of 2x to the fourth minus 16x squared plus 2 also equals positive infinity. So, again, as you plug in numbers closer and closer to negative infinity, and for x, the value of y is going to get larger. The same goes if you plug in values of x towards infinity. the value of y is going to get larger and larger. So there is no absolute maximum here. We only have an absolute minimum, and that absolute minimum is negative 30. Okay, it occurs at two x values. One of them is negative 2, the other is positive 2. Okay, you can try to check your understanding on your own, and then you can unpause the video and we'll look at the critical point theorem. So this critical point theorem, something to note about it is that it can only be used if f has one critical number on the interval. Okay, so what does it say? Suppose a function f is continuous on an interval and we'll call that interval I, okay? And that f has exactly one critical number. In that interval, located at x equals some constant. If f has a relative max, remember we talked about relative maxes in some prior videos, which we found through the first derivative test. And you can also find through the second derivative test. If f has a relative max at x equals c, then this relative max is the absolute maximum. So the highest y value of f on the interval I. And then likewise, if f has a relative minimum at x equals c, then this relative min is the absolute minimum of f on that interval I. Okay, so again, we can only use this theorem if f has one critical number on the interval, and if that function is continuous on the interval, and there's exactly one critical number in that interval, all you have to do is look at the value of c, the constant. What is that y value there? And if the function has a relative max, then this relative max is also the absolute max of f on that interval, okay? Provided there's only one critical number, and then it's a continuous function. And if f has a relative minimum, then that relative minimum is also the absolute minimum. So it's also the lowest point of the function on that interval. Okay, let's look at where we can apply this. So the US and Canadian exchange rate changes daily. The value of the US dollar and Canadian dollars between 2015 and 2020 can be approximated by the function f of t equals negative 0.00244 t cubed plus 0.109 t squared minus 1.53 t plus 7.88, where t is the number of years since 2000. based on this approximation, in what year during this period did the value of the dollar reach its absolute maximum? And what is the maximum value of the dollar during this period? Okay, so we know that we have a polynomial function, and it is defined on the closed interval from 15 to 20, okay, because we're only looking from the years 15 to 20. So since the function is also continuous, we can use the extreme value theorem. So the first thing I need to do is, the question says, in what year during this period did the value of the dollar reach its absolute maximum? And then what is the maximum value of the dollar during this period? So I need to find the first derivative. So to do that, I need to find f of t. Okay, so I'm just going to use the power rule, and you would get negative 0.00732 t squared plus 0.218 t minus 1.53. Okay, I'm going to set that equal to 0. And we're not going to factor it. Instead, we're going to use the quadratic formula. So I would get t equals negative 0.218 plus or minus the square root of 2.18 squared minus 4 times negative 0.00732 times negative 1.53, and then all over 2 times negative 0.00732. And when you do that, you get the following values. You'll get positive 11.13 and 18.5. And again, we're only looking in the interval from 15 to 20 because we only care about from 2015 to 2020. So since 11.13 is not in the interval, we're not going to worry about it for our critical values. So since we only have one critical value, we can apply the critical point theorem, right? So if you think of, again, like we drew number lines, here's 18.5, maybe pick 17 and then 19. And if I plug in 17 into my derivative, I would end up with a positive. So we know the function is increasing there. And then if I plug in 19 into my derivative, you would end up with a negative. So we know the function's decreasing there, right? So since it's increasing and then it's decreasing, that tells me that there's a relative max at t equals 18.5. Okay, so I need to find f of 18.5. I would plug in 18.5 back into the original function, and when I do that, I end up with 1.43 approximately. Okay, so since I just applied the critical point theorem, right, and this tells me when there's one critical value on an interval, when you have a relative max at that point, then it also becomes the absolute maximum at that point. So this is also the absolute max. Okay, so therefore, if I interpreted this, it tells me that about 18.5 years after 2000, so that's mid 2018, right? The US dollar was worth about $1.43 Canadian, so Canadian dollars or CAD, which was also an absolute maximum during this period. The final thing we're going to look at in this video is what's called graphical optimization. So we use graphical optimization in calculus to visually identify extrema of a function by analyzing its graph. It helps when you're estimating critical points, when you need to confirm extrema with the first derivative test, using the second derivative test, absolute extrema, and also real-world applications such as in business, physics, engineering. It helps with things like maximum profits, minimizing costs, or optimizing physical conditions like velocity or area and things like that. Okay, so let's look at an optimization problem here. We want to find the minimum value of the average cost for the given cost function on the given intervals. So I'm given that my cost function is c of x equals x cubed plus 37x plus 250. And I'll find A and I'll leave you all to find B on your own, okay? So we need to find the minimum value of the average cost function. If you'll recall, the average cost function is found by taking the cost function and dividing by the number of items. So here we have x cubed plus 37x plus 250, and I'm going to divide that by x. And x cubed divided by x gives me x squared. And 37x divided by x just gives me 37. And then I get plus 250 over x. Okay, now I want to find the derivative of that average cost function. So that would just be 2x and then minus 250 over x squared. Okay, and if I want to get a common denominator there, let's see, I would multiply this by x squared over x squared. So I would get 2x cubed minus 250 and then over x squared. Okay, I'm going to take that and I'm going to set it equal to 0, which again, you have a fraction equal to 0, so that just means take the numerator and set it equal to 0. And let's see, I can factor a 2 out of there, and I would get x cubed minus 125. And then I would have x cubed minus 125 equals 0. I would add 125 to both sides and then take the cubed root. And the cubed root of 125 is just 5. So x equals 5. So I have my critical value. Again, you've got one critical value, right? So we can use the critical point theorem. And let's pick a number before it and after it. If I plug in 4 into my derivative, I would get a negative, so the function's decreasing. And then when I plug a 6 in to my derivative, I get a positive, so that means it's increasing. So that means there's going to be a relative min here at x equals 5. So then I just need to find c bar, which is the average, right? Which would give me 112. So if I plug 5 back into this original cost function, I get 112. Okay, and that's my relative minimum. And I also need to use my endpoints, which would be 1 and 10. So I'm going to find c bar of 1, c bar of 10. When I plug 1 into the original function, I get 288. And when I plug in 10, I get 162. So as you can see here then, this is your relative min, which is also your absolute min. Okay, you guys can try letter B on your own, and that brings us to the conclusion of this video. Please reach out if you have any questions. I hope you all enjoy the rest of your day.